going to start this lecture advanced reaction engineering. So, today we will discuss the reaction rate with conversion temperature and pressure. So, how that related with each other. So, that we will discuss by considering various reactor, that is batch reactor or flow reactor. So, already we have discussed means the design equation, various reactions, various reactors. So, now whenever we are going to design a reactor, so then the rate equation is very important. So, the rate equations we have to use for the in the design equations to find the volume of the reactor. So, to get the rate equations, it is the simplest way we can express in the rate as a function of conversions. Okay. So, that way if we express, then easily as a desired conversions or specified conversions, we can put this rate equation into the design equations. So, in terms of conversions or in terms of as a function of pressure, temperature. So, then easily we can evaluate the volume, or we can find out the volume. So, here we will discuss how to obtain the rate data, means rate minus R A as a function of conversions for both gas systems and liquid phase system. So, the rate of reactions that is the related with the concentration of the reacting species, that is C A, and the temperature. Usually the rate we express for a particular reaction, so let us say for a first order reaction. So, rate minus R equals to K into C A, and C A that is the concentration, that is the final concentrations after reacting the reactant inside of the reactor. So, when reactions we are conducting, so there may be a number of species, may be not only reactant A, with that there are some other species also may form. So, how reactant depending upon the stoichiometry, so reactions will take place and accordingly the product will form. So, here's rate we can express, that is as a function of concentration as well as temperature also. So, here in this reactions, here you can see reactions rate A is going to product that is reactions, another reactions A plus B that is giving to C plus D, that is irreversible reactions. The here A and B both are the reactant, C and D that is the product. So, here the reactions maybe we can write other form, that is the reversible reactions also. This is the reversible reactions we can see. So, the either the reaction be irreversible or reversible. So, if we know a particular rate of formations of a one component, then rate of formations of other component we can find out. So, by using the relative rate. So, here is the relative rate of the reactions we have written for on the basis of component A, B, C and D. So, minus R A, that is the rate of disappearance of component A, minus R B, that is the rate of disappearance of component B, C, R C and R D, that is respectively component C and D, and here small a, small b, small c, that is the corresponding respective stoichiometric coefficient of that reactions. Okay. So, that you have to put. So, if we want to if we are available minus R A for that these particular reactions, and if we want to rate of formations of R D. So, then simply just we can put minus R A by A equals to R D by R D. So, here if A D minus R A is known, so then R D of rate of formations of that species we can find out. So, now the rate also means the rate equations there are elementary or non-elementary type of depending upon that reaction mechanism. So, we can derive that the rate equations. So, these are the means for any reactions, means whether it is elementary or non-elementary reactions, based on that we can write the rate equation this way, or we can write the this way. This is the non-elementary rate equation, this is the elementary rate equation. There are some other reversible reactions is also there. So, this is the reversible reactions A, B going to C and D. So, the reactions is the reversible reactions. In that case the rate law is reduced to the thermodynamic relationships relating to the reacting species concentrations at equilibrium. So, here this is the rate equations we can write for this type of reversible reactions. When it is in the equilibrium state, then the rate of the rate of disappearance formations, everything should be 0. So, then we can write the rate constant in terms of K c equals to K by K minus A, or Kc we can write in terms of concentrations at equilibrium equals to concentration of C component C, concentration of D and concentration of component A and B, and that way we can write. So, here if we know let us say that equilibrium constant as a particular temperature of that particular reactions. So, then we can find out or we can use these equations here. So, equilibrium constant K c at particular temperature or specified temperature we can find out by putting other parameters in this equations. If it is known and heat of reactions R value, gas constant, these are specified temperature and that standard temperature. So, if it is known then K c value at a specified temperature we can find out, that we can put, and then by that way we can means find out the concentration conversions or other things. Similarly, the rate constant for Arrhenius equation, that way also it is related small k. So, as a function of temperature. So, here we can put temperatures, activation energy, ideal gas constant. So, then k value we can find out using these equations also. Now, what are the various rate equations and how to, depending upon the stoichiometry, the rate equations we can express in terms of concentrations of that particular reactions. So, now if we have a let us say batch reactor. So, then batch reactor if we conduct that particular reactions. So, here how the reactant molecules, let us say this is the reaction that is we are conducting in this batch reactor, this is a batch reactor. So, in this batch reactors, if we, this is a batch reactor. So, here if we conduct the reactions, so here we will charge component A and B inside of the reactors at the beginning T equal to 0, then the number of moles A is Na 0, N 0 is the component B initial moles that is present inside of the reactors. If there is C present at the beginning, then it would be C naught we should mention. So, how many moles of C that we have taken at the beginning of the reactions, or similarly for component D also if we have taken, then that we should put, or otherwise we can consider this is as a 0 at the beginning. And inert component if it is present, let us say if it is gas phase reaction, sometimes nitrogen is used as a means carrier gas for with that particular reactions. That concentration is also important, means how many moles of that inert component is used during reactions. So, that would not take part in the reactions, but that we should mention. So, once the reactions will take place for T time, then number of moles will changes Na naught to Na. This is the at T times. So, these are the number of moles present after let us say the reactions if it takes for 30 minutes, then after 30 minutes we stop the reactions, and if we take out the sample and measure the sample concentration. So, then number of moles present in the reactor that would be unreacted reactant left, NB is the unreacted reactant component B left inside of the reactors, component C that C formed inside of the reactor, similarly D also formed inside of the reactors, and I is the concentration or the moles of inert component present in the reactor. So, here the number of moles means here initially you have taken Na naught, that converted at the final it is changes into Na. So, means the difference would be the number of moles that component are used for that particular reaction, that is the mole used or reacted Na naught into X. If X is the conversions, so then initial that number of moles were taken for that particular reaction. So, then Na naught into X, that is the moles that reacted for this particular reaction. Similarly, for component B also depending upon the stoichiometry ratio. So, number of B that is reacted, that is B by A into Na naught into X, that moles of B consumed. So, here moles remaining inside of the reactor. So, that is Na. So, Na equals to initially you have taken this and that much moles has been reacted during reactions. The subtraction or the differences would be the number of moles remaining inside of the reactor. So, we can write Na equals to Na naught into X. Okay. So, now this is the means way, means here is the actual reactions when we have conducted in the batch reactors. So, here everything means the components A, B that is reactants, component C and D that is the products. So, here there is the species, this is initial concentration, that is the change due to the reactions, and this is remaining, and these are the things we will fill up. So, let us say first component A, initially you have taken Na naught and then A minus Na naught into X, that moles reactant consumed or reacted inside of the reactions, and then the remaining moles of A remains inside of the reactor, that is Na, that is equals to Na naught minus Na naught into x. So, this is the number of moles remaining inside of the reactor. So, here's moles in terms of moles we have find out. So, now we have to find out, or we have to express in terms of conversions or concentrations. Okay. So, then in terms of moles we have obtained for that particular component A. So, next this part we have to fill up, means that we have to express in terms of concentrations of that particular component A. Similarly, for component B also, that much moles of B reacted with A. Initially you have taken this, and this is the number of moles that present inside of the reactors after T time of reactions. Similarly, for component C also we can get this. So, initially if we have taken any number of moles present inside of the reactor at the beginning, then N C naught we should mention. If N C naught equals to, let us say 0.1 moles we have taken to start the reactions, then N C naught we should put. If at the beginning there is no N C, C was not taken for the reaction, then we should put 0. Most of the cases initial concentration of the products is 0. Okay. So, either this part we can put directly 0, or if it is required for the to start the reaction, then we should put. So, for balance we should write this way. Here you should note down, this is the positive and here this is negative, since reactant is these are the reactants A and B, both are the reactant that will be consumed, therefore, it is negative, and here C and D are the product that would form the concentration with the time that would gradually increase, therefore, it is positive sign. Okay. So, then total number of initially we have taken N T naught, if we sum up all these components. So, then N T equals to N T naught equals to initial total number of moles that was taken, and then finally, we have getting the number of moles inside of the reactor, that is N T equals to summation of Na, Nb, N plus Nc plus Nd plus Ni. So, then if you sum of the right hand side components, then it would come this. So, Nt equal to Nt naught plus d by A plus dc by A minus b by A minus 1 first bracket close Na naught into x. So, total number of moles present inside of the reactors. So, here these components in the bracket, this term is the changes of moles. Okay. So, this is the stoichiometry, here 1, here B by A number of moles, here C by A, here D by A. So, here delta, that is we are expressing, that is the changes of total number of moles, that is equals to initially that for product, this is for A, this is the changes per unit moles of A, or delta we can write this way, means total number of changes of moles during reactions per unit moles of A, that is reacted. Okay. And Nt we can write, therefore, Nt equal to Nt naught delta Na0 into x. So, here's the concentrations I said we have to express concentration, the rate equations we have to express, or we are going to express in terms of conversions. Therefore, Ca equals to we can write Na by V, V is the volume of the reactors. So, here's Na equals to Na naught into 1 minus x, that we have derived here. This is Na equals to Na naught into 1 minus x, that is coming from here. Okay. So, then we can put the Na equals to here, and then we can write these equations this way. So, Ca equals to Na naught into 1 minus x divided by V. Okay. So, now the next means this part in the right hand side of this part, this concentration that was empty. So, here we will put individual component concentrations in terms of mole per dmq, means we are including the volume part. Initially it was in terms of moles, now we are expressing in terms of concentration. So, Ca equals to Na by V equals to this, and then we are writing this. Similarly, for component B, component C, component D also we can write this. So, here you can notice, so here if we take out Na naught from the brackets, so then we have to divide Na naught with Nb0. Okay. So, then here Nb naught by Na naught that is equals to, we are writing here theta B. For B indicate the component B, and theta is the ratio of the moles in terms of that specific component divided by component A initial concentration. Similarly, here also this is we can write in terms of mole fractions a ratio for component the desired component with respect to the component A. So, here let us say theta B equals to C B 0 by C A 0. Similarly, theta C equals to concentration of C naught by C A naught. That way we have right. Okay. So, here you can see theta C equal to this, theta D equals to this N D naught by N A naught. So, that way we have expressed. Okay. So, in terms of moles per unit initial moles and per unit volume or volume basis we have written the concentration of individual components. So, now the systems I said it may be a volume changes or there may not be a volume changes, means the reaction may be we can conduct or reaction depending upon the stoichiometry, it may be a constant volume systems or variable volume systems. If we consider that the systems is constant volume, there is no changes of volume. So, at the beginning the volume we have taken and after reactions remain the same volumes of the reacting or product mixture. So, then we can write V equal to V naught. So, now in that equations here V equal to V naught we are substituting here. So, then it would come this way, okay. N A naught into 1 minus x by V naught, capital V naught, that equals to we can write C A naught into 1 minus x, C A naught equals to N A naught by V naught. Okay. So, then therefore, we are replacing this C A naught V naught into C A naught. So, then we can write C A equals to C A naught into 1 minus x. Similarly, for component B also we can write this N A naught into V naught, that is equals to C A naught, and this is theta B minus V by A into x, and for component C also we can write C C, that is the concentration of component C, we can write here also we are substituting V equals to V naught, this V equals to V naught we are substituting. So, then N A naught by V naught, that is equals to C A naught. So, this is the concentrations or for individual component that we can write. Here you can see that theta B, theta C, what that is indicate. Here theta A we have not written, that is equals to N A naught by N A naught, okay, that is equals to 1. Therefore, we have not written here, but we can write that way also, but what would be this. So, now we know for the batch system. So, that now the table would be complete. Okay. So, for component A initial the amount changes, the remaining and then the concentration of these components we can write this way, component B this, component C, component D also, in terms of known component, that is initial concentration of A and conversions in terms of that the concentration we are expressing. Okay. So, now for the reaction systems, if we want to write the rate law, rate equations. So, rate usually for a reactions we can write minus R equals to K into C A into C B. K is the reaction rate constant, C A is the concentration of that component A, C B is the concentration of the component B. So, now we know C A and C B value from the stoichiometry table or this table. So, C A and C B we can, this is equals to C A and this is equals to C B. Okay. So, now these two terms we can substitute here in this rate equation. So, then after rearranging, so we will get this. So, this here you can see the minus R A, that is the left hand side, that is the rate of the reactions for this particular reactions. Yeah, right hand side C A naught, that is the known component, and theta B, that is the ratio of component B by component A initial mole ratio, that we know at the beginning. So, when we have started the reactions, so initially how many moles of component A and component B that was taken for that particular reaction. So, then theta B is known, and B, from the stoichiometry table B by A also is known. So, then once everything is known, so here only this equation is coming rate as a function of x. So, therefore, if we want to get a rate for that particular reactions, so x value we can put like this way. So, then corresponding if we put here x value 1 by 1 0, 0.1, 0.2, 0.5, 0.8, 0.1, then corresponding minus R A will get. So, if we plot this, so then the plot would be like this. If it is plug flow reactors, So, rate means inverse of rate. So, if F A naught you know, so that is equals to C A naught into V naught. So, if we know, so that we will discuss later. So, any reactor. So, if we want to get minus R A and X A if you want to plot. So, then this curve will come. So, from here if we means change the conversions, the corresponding rate also accordingly we change, that way this data we can use for any other reactor to get or design or to find out the volume of the reactor. Similarly, here CSTA reactor and PFR reactors, that rate data was used in terms of conversions. So, here this area and this area for PFR reactor. So, that we have discussed in our last class also. So, this is the way, means a rate we can express in terms of conversions. So, that way we can express. Okay. So, similarly, means for a flow systems or continuous systems also we can write the means concentrations or that particular means rate equations, means let us say this is the rate equations. So, if we have a flow systems, so flow systems also similarly we can express the concentrations in terms of conversions, and then the rate of that particular reactions for continuous flow systems. We can similarly we can individual component concentrations in terms of conversions we can write and we can express that, and then that we can put inside of the rate equations, and then finally we can get the rate as a function of conversion of that particular components. Okay. Similarly, we have made this table. See here let us say reactant A, reactant B, reactant C, reactant D was there. So, here in the flow system and earlier one, that one was the batch system. In batch systems always we use in terms of concentration or moles. If we look into this, here's initial concentration that was used for this particular reaction, that was in terms of moles. Since it was the batch systems, in batch systems whenever the component concentrations will write that is in terms of moles. Okay. Here in terms of moles we have used, and in case of the batch system, here you see initial mole per unit time, it would be initially this is the molar flow rates of component A, here the molar flow rate of component B, here molar flow rate of component C, component D and component I, that is the inert. I means inert component, that may be waters or any inert, if it is liquid phase reactions we can consider that is liquid phase reaction water we can consider as a inert component for that particular reaction if it does not take part in the reaction. And if it is gaseous system, so similarly we can say that nitrogen, helium, argon, any gaseous component that are usually used for as a inert material to flow that reactant component or pass the reactants or feed the reactant component into the reactor. So, then here the molar flow rate are usually in case of the continuous system the mole in or moles out, that usually expressed in terms of molar flow rates. So, means this is in, this is out. So, it is mole per unit time, mole per unit time. So, here initially that much moles of reactant component A, B, C were taken and D was taken for that particular reaction. So, after let us say changes, means when the means reactions will take place inside of the reactor. So, here inside of the reactor reactions will take place. After that, from the exit or outlet of the reactors, if you want to means get the concentrations or take out the samples, and if you want to measure the concentrations. So, then the number of mole changes per unit times, that would be minus F naught into X for component A. Similarly, for component B also, that would be minus B by A F A naught into X, and for component C, C A by F A naught into X, and for component D, D by A F A naught into X, that number of moles per unit time, that would be changes total times when that reactant molecule spent inside of the reactor and that take part in the reactions, that amount of the moles per unit time, that changes would be there. In case of the inert there is no changes. So, then the remaining components inside of the reactors or after reactions from the exit of the reactor that we are getting, F A equals to F A naught minus F A naught into x. Initially it was this, and that much amount it is take part in the reactions, and if we subtract from these to this, then that would be the number of moles that is leaving from the reactors. Similarly, for component B also we can write the number of moles per unit time, that is the changes, or remaining means from the outside of the reactors we are getting this for component D, and for in case of the inert component there is no changes. So, here if we sum up all these components, that is the initially you have taken the total number of moles, that was F T naught, and finally after reactions take place, that all the reactant component coming out from the reactor system. So, the moles leaving from the reactors from the outside or exit of the reactors, that we are getting, that is F T. So, F T equal to F T 0 plus similarly this changes of number of moles into F A naught into x. So, we can write this in terms of F T equals to F T naught plus delta into F A naught into x, and here now means this part is left. So, this part we have to means derived, or we have to changes that molar flow rate in terms of concentrations, then we can put it here, then the concentrations would come mole per dmq. Okay. So, that part we needs, that we have to put in the red equations, and that we have to express in terms of conversions. Okay. So, now concentrations we can express in terms of molar flow rate by volumetric flow rate. Here V is the volumetric flow rate. Volumetric flow rate. So, that is the volumetric flow rate. So, here F is the molar flow rate and small v, that is the volumetric flow rate. So, if we divide F A by V, so then that is coming the concentration, that is the C A. So, here unit would be mole per liter concentration units, but F A that unit mole per unit times, or volumetric flow rate liter per unit time. So, here for component A we can write F A by V, a small v, that is equals to F A naught into F A naught into x, or F A naught into 1 minus x divided with small v. Okay, that is the volumetric flow rates. So, similarly for component B also we can write this. Here if we take out F A naught from here to brackets and make it into this way. So, then F A naught is coming out theta b into 1 minus b by a into x. Here theta b that I already said, theta b equals to F b naught by F A naught, that equivalents to this. So, here the expressions we are writing this way. Similarly, for component C also we can write F A naught theta c into 1 plus c by a into x by small v, volumetric flow rate. So, similarly for component D also we can write the concentration in terms of initial molar flow rate of component A, theta d 1 plus d by a into x by small v, volumetric flow rates. Okay. So, now the concentration we have written this way. Now for the liquid, if the flow system means in here the reactor is the flow reactor or continuous reactor. So, here the reactions we can conduct in gas phase, both the reactant is in the gas phase, or maybe both the reactants are in the liquid phase. So, if in usually liquid phase, when the reaction is there, here the volume changes usually negligible, means volumetric flow rate whatever that is the changing, then small v equal to small v naught. So, that way we can write. So, here in case of the liquid system the volume change is not significant, but in case of the gas systems reactions when there is going on. So, there if there is a changes of volumes, if slightly changes in the temperature, pressure in the system. So, volume changes we can observe, even as per stoichiometry also, if there is changes in the volumes. So, that would affect overall conversions rate or other things. So, therefore, if we consider the systems is the liquid phase, means all the reactants are liquids and the reactions is taking place liquid phase. So, then V equals to small v equals to small v naught, we can put it here. Okay. So, here similarly for component B also V equals to V naught, we can put it here, and for component C, component D also small v we can replace the small v into small v naught. Okay. So, here you can see we have replaced this small v into v naught. So, then after taking outside f a naught v naught. So, that is the equals to c naught into 1 minus x. So, this is the flow system. So, similarly for component B, component C and component D also we can write the concentrations in terms of individual concentration of reactant concentration A in terms of theta B, theta C and theta D and corresponding concentration and mole ratio or stoichiometry ratio. That way we can write. So, if the gas systems is there, so in that case also which I said there is a changes of volumetric flow rate or volume changes is observed in case of the gas system, and therefore, the total moles, temperature, pressures also that would affect overall the reaction. So, in case of the batch systems constant there is no changes. If there is batch systems, but volume is variables, then volume we can write this way, and if flow system is there, volumetric flow rate for constant system we can write this, and if it is variable volume systems we can write v equals to v naught into 1 plus E into x. Okay. So, here v is the volumes, small v is the volumetric flow rate. So, here the systems may be temperature and pressure both are constant in that case also, but here maybe volume changes is observed if it is batch systems or flow systems, that way we can express or we can write the volume changes. So, now in the case of the gas phase reactions, I said the expressions of volume changes as a function of conversions. So, let us say the at any t times. So, this is the equations of states that we can write P v equal to Z n t into R t, and for at any time t equal to 0. So, we can write this. Okay. So, here P naught is the at t time any time t equal to 0, when time t equal to 0. So, P naught V naught equals to J naught N t naught R T naught. So, here Z equals to compressibility factors, N t is the total number of moles at time t and N t naught at time t equal to 0. So, corresponding volume, pressure and temperature of the systems and ideal gas constant. So, if we take ratio of these two, so then we can write this as this. Okay. So, left hand side that is the volume, and then at pressure, temperatures, compressibility factors and N t naught, that way we can write. So, here we have derived this just total number of moles equals to in our stoichiometric tables when we have developed. So, there you can see the here we have derived this total number of moles presents N t equals to N t naught into this stoichiometry coefficient differences into n naught into x. So, here this part equals to we can put as a delta, that is the changes of number of moles of reactions per unit moles of A. Okay. So, then this N t equals to total number of moles, N t 0 initially total number of moles, delta equals to this. Okay. The changes in total number of moles per unit moles of A reactants. Okay. So, here we can write this. So, these equations we can express this way. So, if you divided both side N t naughts, so then it would come this. So, then right hand side we can write this way. Okay. So, 1 plus delta y a naught x, here y a naught equal to the mole fractions. Okay. Y a naught equals to n a naught by N t naught. Okay. So, here we are expressing these equations, okay, N t by N t naught in terms of this part equals to this is the fraction volume change, delta is the changes of moles and this is the mole fractions. Okay. So, here N t by N t naught we are expressing in terms of 1 plus epsilon into x, or epsilon we can write N t by N t naught by N t naught into x, that is the changes of total number of moles for complete conversions and divided by total moles fed. Okay. So, here this part we have means just we have derived this from the mole changes, and this is for at two different times the changes of volumes t equal to 0 to t equal to t times. So, here from the ideal gas equation or equation of continuity, there V equals to this way we can write, and this we have derived from the stoichiometry tables. We can substitute this here in these equations, and we assume that or considering that there is no changes, means Z compressibility factor for that system. So, Z 0 equals to Z, for simplicity we are writing this. So, then this part will be eliminated and this part will be substituted here. So, then these equations we can write V equals to V naught, P naught by P, and this N T by N T naught we are substituted with this, and this temperature part would remain this. So, volume that is change means as a function of initially this was the volume and this is the pressure part and this is the temperature part, this is the initial and this is that specified temperature and this is the fraction volume change and this is the conversions. So, this way you can write for the batch systems where the volume would be changes, and similarly for flow system also here the volumetric flow rate as a function of conversion. Similarly, we can write this is small v that is equals to this way we can P into 1 plus epsilon x T by T naught. Okay. So, this way we can write similarly here V is the small v is the volumetric flow rate of the gas at any time, that we can write this way. So, here the detail means derivation for this V, how small v equals to V naught into this, and P pressure and temperature how they are related, that we have derived here. So, you can see that. So, similarly we have derived. So, we can use that. So, now in the batch system, if there is a, now we are discussing about the volume changes is there in the gas system, batch systems or gas phase reactions. In that case the concentration of the individual component we can write, here's volume changes is there, these equations we have derived, we are just substituting here. Okay. So, then concentrations, the final concentration of the component A after reactions we can write Ca naught, and pressure, temperature and conversions and fractional volume change, that way we can write. Similarly, for component B also we can derive this, component C also we can derive this, component C also we can derive this. So, here this V we have to substitute here. So, then the equations will be come in terms of similar equations will derived. Okay. So, and for that was the for batch system, and for flow systems also volumetric flow rate we can put it in the these equations. Here V equals to V naught we put, and F A naught by V naught, that would be C naught. Okay. So, that is why it is coming in terms of this. So, here V equal to this, and if we substitute the small v here, so it would be in terms of pressure, temperature, conversion and concentration. Similarly, for component B and C and D also we can express the concentration, final concentration of the component, individual component in terms of temperature, pressures and conversions and initial concentration, fractional volume change, that way we can express. So, flow system and batch system, the concentrations we have expressed, we have considered the volume changes, temperature changes, pressure changes. So, now we are coming into the rate law, rate equations. This is the simplest rate equations, minus R equals to K into Ca Cb. So, now Ca and Cb that we have derived from this equation Ca and Cb. So, this we will put here. Okay. So, then after simplifications we can get it this. So, this is the rate equations minus Ra in terms of so many parameters in the right hand side is there. So, if all these parameters are known, then the rate of the reactions that we can find out. Okay. And minus Ra we can find out. Okay. So, by putting all these parameters or components in the right hand side, so if we know for this particular reactions rate constant, if we know initial concentration for these reactions we know, theta b is know, that is the ratio of the moles for component B to component A, stoichiometric coefficient ratio we know, as temperature is known, initial final temperature, and pressure is known, initial final pressure if there is any changes, fraction volume change is known. Then for a specified conversions, so that we can develop this table. Okay. So, this table is important to derive or design a particular reactor to find out the volumes of that particular reactor. So, then similarly that data we can use to find out if it is the reaction is conducted in a PFR reactor, plug flow reactor, then the corresponding volume area under these curves we can find out within that specified conversions or desired conversions. By that way you can find out the volume of the PFR. Similarly, for CSTR reactor also we can find out the volume of that CSTR. If we know the rate versus conversions this table. Okay. So, here how to derive this, that we have discussed. I think now it is thank you.